The first exam will cover everything before Laplace Transforms. So Laplace Transforms is exam 2, which doesn't mean you ignore it now because you haven't had exam 1. Because in this class, you probably noticed it's not a good idea to fall behind because there's a lot of new math. So you really want to keep up with the math as we're doing it in class, or at most in the evening between classes. You certainly don't want to fall a couple of weeks behind because you'll never catch up. Especially starting now with Laplace Transforms, the stuff we did before, you had in ODEs in your differential equations class, and it was still a bit challenging. The math we're going to do now from this class for the next few classes is math you've never had before. So if you don't try to keep up with it now, you're not going to be able to learn it on your own. The idea is to try to learn it with me, and if you have questions, to ask me the questions before I get 100 steps ahead of you. When I'm 1 step ahead of you, you want to ask the questions, not wait till I'm 100 steps ahead. Okay, so that's just sort of, I want to make sure that I know the habit. I was a student too. If I have an exam that covers the material till here, I wouldn't worry about the material after that till after the exam. But in this class, that's a really bad idea. So please don't do that. Okay, so we started talking last time about Laplace Transforms as a method that makes it a lot easier to solve these linear ordinary differential equations. Linear constant coefficient ordinary differential equations. It makes it much easier. And we're just starting that development. So what the idea here was if we have a function of t, time, we go from time being, t being the independent variable, to some other variable s. And usually we refer to it as going from the time domain to the s domain, whatever that is. So, and we define f of s. When you see a colon before an equal sign, that means it's a definition. That's a standard notation for definition. As the integral from 0 to infinity to the minus st f of t dt. So clearly for this to exist, f of t has to can't grow faster than e to the minus st shrinks. Otherwise the integral won't converge. So that's clearly a necessary condition, but not a sufficient condition. We did a few examples where you calculate theta of t. Remember, theta is a step function. We take the Laplace transform of that, we got 1 over s. And the step function is what we've been using all semester for how, for example, the inlet concentration varied or the bidimensional flow rate varied. We always said it was a constant for t less than 0, and t greater than 0 would switch to another constant. So that's called the Heaviside function, just notation, and it's written as theta of t. And when I take a tilde on top, that always means Laplace transform. So we calculated theta tilde of the Laplace transform of the step function is 1 over s if the step function is at 0. If the step function is somewhere else, well, we'll talk about that in a second. If we take the Laplace transform of e to the a t, we got 1 over s minus a. The Laplace transform of sine was omega over sine squared plus omega squared. And you have a table that I've been giving out that's in your textbook that gives you a lot of these pairs of the function of t on the left and the Laplace transform f tilde of s on the right. And generally, here I'm deriving some of them, but in practice, you really use the table as much as you can instead of doing the integrals. That is, when you want to go from t to s, you look for the f of t on the left, and then write the f tilde of s. And then when you do the algebra and come up with an answer in terms of s, you look for it here and try to go backwards to get f of t. So finally we did, the last thing we did is we looked at theta of t minus theta of t plus tp. That is divided by tp. So this is a step function of t. This is a step function of t plus tp. Since I'm subtracting it, I get a little box here. Divided by tp, so that way the height of the box is 1 over tp, and the width of the box is tp. So therefore the area of this box is 1 over Tp times Tp, which is just 1. And we see that the Laplace transform of that is 1 minus e to the minus STP over STP. Now, why am I interested in that? Because what I'd like to do is I'd like to take the limit as Tp goes to 0 of this thing on top of what I have here. Now, why do I want to do, what happens when I do that? When I do that, the width of this box goes to 0, but the height goes to infinity in such a way that the area is always 1. Is that clear? And that's weird, because when the width goes to 0, the width, the area, usually the area of a point, under a point, over a point is 0. But if I had a function, and if I have a function, if you give me x, I should be able to tell you what f of x is. So this is not a function, it's called a generalized function. And this limit is called the Dirac delta, delta t, and it's called the Dirac delta. For Paul H. and Maurice Dirac, who was a physicist in the 20th century, he died about 20 years ago, not that long, and he was really a pioneer in relativistic quantum mechanics. The Dirac equation, if you take a class in quantum mechanics, in advanced quantum mechanics, you'll find the Dirac equation, which is an equation for relativistic quantum mechanics. But in the course of his studies, he found it was useful to define this generalized function called the Dirac delta. And let's see what happens when I do this. Well, notice I have, when Tp goes to 0, then I have 1 minus 1 in the numerator. I get 0 in the numerator and 0 in the denominator. So whose rule do I need to use if I want to take the limit of 0 over 0? Calculus, whose rule do I use? L'Hopital. So I take the derivative with respect to Tp of the denominator as s, and I take the derivative with respect to Tp of the numerator. If I take the derivative with respect to Tp of the numerator, I get e to the minus STP with a minus, times the derivative of this thing with respect to Tp, which is minus s. The minuses cancel, the s's cancel, and I take the limit as Tp goes to 0 of this, and I get 1. So I know that the Laplace transform of the Dirac delta distribution is equal to 1. Delta is called either a distribution or a generalized function. So that's just the terminology. It's not a function because I can't tell you what delta of 0 is. It's infinity. If I had a function, I could always tell you what its value is at any point. Now, why is the Dirac delta useful? Well, let's notice, let's say if I have any old function g of t, and I take delta of t minus dp, dt, and let's say I go from 0 to infinity. So let's say I have any old function g, and I multiply it by delta, and I want to integrate it. Where here this delta, instead of being at 0, is at some tp. Or I can call it t star, it doesn't have to be tp. I don't want to confuse it with this t. Just any t star. Well, let's see what that is. That's equal to the limit, the integral from 0 to infinity, g of t, times the limit as Tp goes to 0 of theta of t star minus theta of t star plus Tp divided by Tp dt. Let's see, t minus t star. No, that's not right. It should be, I need this to be a function of t. So, t, yeah, t plus t star. Let's rewrite it. Now, if I can take the limit, now the integral itself is a limit, so all I did is I plugged in for delta here. if I can, the integral is itself a limit. If I can pull this limit outside of the integral, and that involves mathematics beyond the scope of this course. But assuming I can take this limit outside, let's see what I would get there. And I would get the limit as Tp goes to 0 of the integral from 0 to infinity g of t times theta of t plus t star minus Tp minus theta of t plus t star over Tp dt. Now let's see what this is. Notice that this thing, what I have in here, is a step function from t plus t star plus to t plus t star plus Tp. It's a step function. Yep.
How do you get from t minus t star to then t plus t star?
Okay, so yeah, maybe I should make it t minus t star minus Tp. T minus t star. I should follow this if I'm going to do t minus t star. Thanks, it was my mistake. T minus t star. Yeah. Okay, thank you. Okay, so this is t star, and this is t star plus Tp. So remember, theta of t minus t star is when t is equal to t star, I have the step. So that's when t is equal to t star, I have the step. And here, it's t minus t star plus Tp. So I go further Tp. Okay, so now I took the limit outside. Now let's see what this says. This says I'm 0 for t less than t star, and I'm 0 for t greater than t star plus Tp. So this is the same thing as the limit as Tp goes to 0 of the integral from t star to t star plus Tp of g of t. And in this region, this function is just 1 over Tp. So is that clear? This thing is a step function. So this whole thing, which is equal to 0 out here, 0 out here, and in this region is 1 over Tp. So I just 1 over Tp, and I just took the t and t star to t star plus Tp. Okay, well this is a constant, it comes out. And if gt is continuous, so if gt is continuous, so here's g, for example, over a small enough region, g can't change much because it's continuous. So if this region is thin enough, from t star to t star plus Tp, then g doesn't change much. And in fact, if it's thin enough, I can just approximate this by g of t star. So if this is almost a constant, I can pull it out. And I just have the integral from t star to t star plus Tp dt. And this thing, dt, this will just give me a thickness, this integral will just give me Tp. Because I'm just integrating dt from t star plus Tp to t star. So the Tp's cancel, and I just get g of t star. So what have we shown? What we've shown is that this thing is just equal to g of t star. And that's why this is really, the delta is really useful. If I integrate g of t over a delta, I just get the value of g of t at where the pulse is at g of t star. So this makes it particularly useful, why the delta is very useful. Are there any questions about it? Questions? Okay, what's the next thing? Okay, so let's see why Laplace transforms are useful. Let's look at, and here the next couple of lines are going to tell us why Laplace transforms are useful. Let's say I want to take the Laplace transform of the f dt. I know what the Laplace transform of these f's are, but what about the f dt? Well, this is equal to the integral of the f dt, when I write it this way, e to the minus st df dt, dt, from 0 to infinity. That's the definition. Well, this begs for us to do integration by parts. Let's call this dv and this u. Then du is minus s e to the minus st dt, and v is just f. So this is equal to uv, e to the minus st times f from 0 to infinity, minus the integral of v du, f s e to the minus st dt from 0 to infinity, where the minuses cancel. The minus v du and the minus u. So let's evaluate this. At infinity, this is 0, because the e to the minus at infinity is 0. At 0, this is just f of 0, minus f of 0. So what, and this thing is nothing more than f tilde. So what I get is s f tilde of s minus f of 0. And this is really important. Why is it important? Because when I have a differential equation with derivatives, and I take the Laplace transform, the derivatives disappear, and I just get an algebraic equation. And we're much better at solving algebraic equations than we are differential equations. Similarly, if I have an integral, the integral of f of t dt, tilde, well, that's equal to the integral from 0 to infinity. Let's call this t prime. Oh, it's t prime, 0 to t prime. Okay, it's actually what I call t prime here and then t. So it's the integral e to the minus st dt, the integral from 0 to t, f of t prime dt prime. I use a different t prime because the limit makes it a function of t, and that's what I'm integrating to take the Laplace transform. Now there are two ways I can do this. Let's just do it by integration by parts. I'll let this thing be u, and this thing be dv. So in this case, du, well, du by the fundamental theorem of calculus, if this is the only time you have is here. So the derivative of this is the integrand evaluated at the top limit times the derivative of the top limit. But the dt is 1. So du is f of t dt. And v is e to the minus st divided by minus s. So again, this thing is equal to uv. uv is equal to, u is the integral from 0 to t, f prime dt prime, times v, e to the minus st over minus s from 0 to infinity, minus the integral of v du. The integral of v du is e to the minus st divided by s, with a plus, times f of t dt, from 0 to infinity. So let's evaluate that. At infinity, this is 0 because e to the minus s infinity is 0. At 0, this is 0 because the integral from 0 to 0 is 0. So both of these give me 0. And I'm just left with 1 over s times f tilde of s. Because the 1 over s comes out. And this is just f tilde. So I have two important results there. Actually, they're all important. But the first one is df dt tilde is equal to s f tilde of s minus f of 0. And the second one is the integral of f of p prime into p prime from 0 to t tilde is equal to f tilde of s over s. So notice what's interesting here is the derivative seems to both turn into a factor of s, and an integral seems to turn into a 1 over s. The only difference is I can initial condition. So those are two very important results. Are there any questions on that? And that's why this is useful, because when we solve differential equations, instead of going through the whole rigmarole of solving the differential equation with the method of ordinary differential equations, we can turn differential equations and integral equations into algebraic equations. And algebra we're still pretty good at. So, and then we just need the table to go backwards. So why don't we look at a couple of examples? So examples we've done already, and let's just see how they're much easier. Let's look at the CSTR with no reaction. And where I have a step change in C8. Is that the problem I want to do? Step change in C8? C8, yeah. Step change, C8. Okay, so remember how we do it. We start at the exact equation. So we have dCA dt is equal to CA in minus CA over tau. And there's no reaction, so that's it. Now I don't have to linearize this because it's linear already. So then I look at the initial condition, which was steady state. And that was dCA at t equals 0, t less than 0, dt. That happened to be 0. It was equal to CA in at t less than 0, minus CA at t less than 0, over tau. And now I subtract. When I subtract, CA minus CA t less than 0 is CA prime. And that's equal to CA in minus CA in t less than 0, CA in prime, minus CA prime divided by tau. So far, it's exactly what we've been doing before, except when we did it initially, we didn't bother with the primes. But now we know we should always do it with the primes. So now I rewrite this. I write dCA prime dt plus CA prime over tau is equal to CA in prime over tau. And now I'm going to, instead of starting to solve this with the formula we had at this, on top of this blackboard for a couple of weeks, I'm going to do it with Laplace transforms. So if I Laplace transform this, I have S CA prime tilde plus CA prime tilde over tau, which, let's just factor that out. I've got CA prime tilde times S plus 1 over tau. S plus 1 over tau is 1 plus S tau over tau. Is equal to CA in prime tilde over tau. But if CA in prime is a step function, that's equal to CA in prime divided by S. Because if this is a step function, then if this is a step function, then the Laplace transform the step function to 1 over S. Okay, so now I have this thing is equal to this thing. And let's solve for CA prime tilde. CA prime tilde is equal to CA in prime times, and notice I can cancel the taus, so I just have divided by S times 1 plus S tau. Is that clear? So I took this equals this, I cancel the taus, and I divide it by 1 plus S tau. So I have 1 over S, 1 over S, 1 plus S tau. Now, instead of looking at doing complicated math, I look in my table. which everyone should have picked one up here. I made enough copies for everybody. And if you look at, it's also your textbook, line 5. Line 5, I have AS plus 1 over S times 1 plus S tau. So that's the same thing as this, except A is 0, or A is equal to 0. So from line 5, I get CA prime of T is equal to, the constant comes along to the right, and 1 over S times 1 over 1 plus S tau gives me 1 plus, well, plus A is 0, minus tau over tau is minus 1, minus e to the minus S, e to the minus T over tau. And that's the same result we got before. But we didn't have to integrate differential equations, we just used the table. Question? Okay, let's do one that's another one that we've done before, but where the algebra was starting to get a little hairier. Let's say I have two CSVRs in series. Here I have CA in, CA1, CA2. And again, this thing is a step function. So remember, we had a lot of algebra with that one. And there were two separate cases where the volume 1 and V2 were the same and V1 and V2 were different. So why don't we go through and do that? Well, we have the same governing equation here. Let's just rewrite it. Exactly. CAI, here I is 1 or 2, is CA in sub I minus CAI over tau I minus KCAI. Now, when I is 2, CA in I is just CA1. So let's just note that what comes into reactor 1 is CA in, what comes into reactor 2 is CA1. And now, at this initial condition steady state, dCAI t less than 0, t is CA in I t less than 0, minus CAI t less than 0, over tau I, minus K CAI t less than 0. And now I subtract, and I get dCAI prime t is equal to CAI in prime minus CAI prime over tau I minus KCAI prime.
Sorry, I don't understand.
I can be 1 or 2 because I have two reactors in series. So now I bring all the CAI primes to one side of the equation. dCAI prime dt plus K plus 1 over tau. K plus 1 over tau is 1 plus K tau I over tau I times CA prime. CAI prime is equal to CAI in prime over tau I. So it's the same algebra I did before, but I have this extra KCAI. Okay, so let's now Laplace transform. So now I have CAI prime tilde times S plus 1 plus K tau I over tau I is equal to CAI in prime over tau I. So far, so good. I just Laplace transform on the left side of this. And now, let's just deal with this. So, if you recall, what I tend to find in the table is I tend to find things like 1 plus S tau. That seems to be things I typically find. So, what I want to do is I want to make this a 1. So in order to make this a 1, I'm going to rewrite this as CAI prime tilde. And I'm going to multiply by tau over 1 plus KI tau. Tau I over 1 plus K tau. And if I do that, what do I get? here I get 1 plus k tau I over tau I s plus 1. So all I did is I factored this out. And that's equal to CAI in prime tau tau I. And now I'm going to bring this to the other side of the equation. So I'm going to solve for CAI prime tilde. CAI prime tilde is equal to CAI in prime tilde over tau tau. That was that. And now I'm going to multiply by 1 plus k tau I over tau I. Am I doing this right? Yes?
Should we factor 1 plus k tau over tau to get 1?
Yeah, I think I did the algebra wrong. So I factor out 1 plus k tau I over tau I. Factor that. And then here I get tau I over 1 plus k tau I. Thank you. That's what I get for not looking at it. And now this is opposite. So this comes tau I over 1 plus k tau I. So I move this to the other side of the equation. And I also divide by 1 plus sti, where ti is equal to tau I over 1 plus k tau I. We saw that before. So I call this thing ti. So I divide this out, I get 1 plus sti. And otherwise, I just divided this thing out, and then tau I out. Okay, ready? We're all with me? So now, let's do the first reactor. In the first reactor, when I is equal to 1, then CAI in prime is equal to tilde, well, CI in prime, tilde is equal to C in prime divided by x, because it's just a step function. Because I just had a step function change in the input. So if that's the case, then I have CA1 prime tilde is CA in prime divided by times 1 plus k tau I times 1 over s, 1 plus st, 1 plus st. So what did I do? This came along for the ride, this came along for the ride, and I just noticed that CA in prime tilde was 1 over s times CA in prime. Okay, so now, no big surprise, the first reactor kind of behaves just like this one. That is, I go back to line 5 of the table, and I notice that I'm looking for 1 over s times 1 plus st, which is exactly what I was looking for over here, but instead of tau, I have t. So I have the same result. This is equal to CA1 prime of t from the table, again line 5, is equal to CA in prime divided by 1 plus k tau 1 times 1 minus e to the minus t over t1, which is a result we've had before. And let's notice that we can look at what Kp is. Kp, remember, is Ca out, the out one, which is Ca1 prime over Ca in prime at steady state. So steady state is when t goes to infinity. So if I divide this out and then let t go to infinity, this just becomes 1. And I just get 1 over 1 plus k tau 1. Kp1 is 1 over 1 plus k tau 1. And so therefore I can write this as Ca in prime times Kb times 1 minus e to the minus 2 over t1. So this is the same result we got before, but so far the algebra was about the same as we did before. The complication in the algebra last time was in the second reactor. And I'm going to show you that the second reactor is really easy to do with Laplace transforms. So, by the way, this is the email of the grader for this class. I'm not sure if she's a grader or a TA. We haven't figured that out yet, but she's at least going to go through your homeworks. She's very strict on deadlines. So there's a homework due today, you have to make sure you get it in today, and you have to make sure that all the previous homeworks were in. Because it's important to, let's recap. The only way you learn the material is by doing the homework. I know all the teachers say it, but it's true. When it's math, the only way you learn is by doing. Going to class is like watching Control on television. You're watching the Control show on television. But you can't do Control until you actually work it out yourself. So you learn from television and network, internet, and then you do it yourself. So please do the homework. The homeworks will be graded. Now, the homeworks will not be graded 0 to 100. Each problem will be graded 0, 1, or 2. 0 means you have no idea what you're doing. 1 means you sort of have an idea what you're doing. And 2 means you're on the right track. You don't have to get the right answer to get a 2. The reason I grade this way is, first, I don't want a lot of pressure on you for homeworks. I want you to do the homeworks and learn from the homeworks. But I still have to keep track who's doing a good job. And also, I want to not give you any incentive to copy. If you were being graded 0 to 100, one person would do the homework and everyone would copy it from you. But since it doesn't matter if you get it completely right or you're just on the right track, you have the incentive to do it yourself. Now, when I say do it yourself, you're welcome to work as groups on the homework. Work together, but then to figure it out. But then write it up yourself. Write it up yourself. Don't copy someone else's write-up. You can work it out in groups. Homeworks, you're supposed to teach each other. It's okay to work together, not on exams, but on homeworks. But then write it up yourself. Okay, so I kind of need this blackboard space, so everyone has it. I'm going to erase it. What? You have to speak slowly with the mouse. Frankie. That's the name she uses. It's not the official name. I think her official name is Breslin, but she doesn't want to be called Breslin. Okay, so why don't we do the second reactor? We already have the equation. The only difference is CA1 even prime. A1 in CA2 in prime is equal to CA1. Because what comes CA1 prime. Because what comes into reactor 2 is what left reactor 1. So this tells me that CA from this equation, this one, CA2 prime tilde is equal to CA1 prime tilde over 1 plus k tau 2 over 1 plus s. That's immediately this equation, what I is equal to 2. Now I have to plug in for what CA1 prime tilde was. Well, CA1 prime tilde was this. But remember CA1 prime tilde, here it is this. So this is equal to CA in prime over 1 plus k tau 1. 1 over s, 1 plus s t1. That's all CA in prime tilde. Now I have a 1 plus k tau 2 from here, and a 1 over 1 plus s t2 here. Is that clear? CA2 prime tilde. So I have a bunch of constants times this thing. And now let's do both cases separately. First, let's look at the case where V1 is equal to V2, which means that tau 1 is tau 2, which means that T1 is T2. So in that case, case A, CA2 prime tilde is CA in prime over 1 plus k tau squared If tau 1 and tau 2 are the same, I don't need a subscript. And 1 over s, 1 plus st squared. So that tells me that CA2 prime of t. I need to look for something like that in the table. Can anyone find a line that has something that looks like that? Line 8. So if I look at line 8, again for line 8, with a is equal to 0, I just get the constants come along to the right. And then I get 1 plus a is 0 minus tau over tau squared minus tau, t over tau. Minus 1, let's see. Minus 1 times e to the minus t over tau. T over tau. So if I got that right, 1 plus, there should be 1 plus, and 1 minus. No, I think it's, let's get this right. So 1 plus, and which is 1 minus 1 plus t over tau. So is that right? 1 minus, so I got plus, I got minus 1 to minus t over tau. Yeah. So that's the solution without much algebra. Let's do the case T1 and T2 are different. V1 not equal to V2. So tau 1 not equal to tau 2. And T1 not equal to T2. So now I have, here's the, I have CA2 prime of T. The constants come along to the right. CA in prime over 1 plus k tau 1, 1 plus k tau 2. And now I have to look for something like this. Do you see a line in the table that has something that looks like 1 over s times 1 over 1 plus st1, 1 over st2? Line 10. So let's just, this was line 8, and this is line 10. So from line 10, again with a is equal to 0, I have 1 plus t1 over t2 minus t1, e to the minus t over t1, minus t2 over t2 minus t1, e to the minus t over t2. So immediately I have a solution, and I didn't have to go through all that nasty algebra. I just read it right off the table. So do you see the advantage now of using Laplace transforms for one advantage of it? It makes these solutions much, much easier. Anything else I want to say about that? Yeah, okay. So, yeah, I do want to get to Kp. So, again, let's look at what Kp is here. In this case, Kp is this guy over this guy at steady state. At steady state, this is 0, this is 0, I'm just getting 1. So here I have Kp for Kp2 is 1 over 1 plus k tau 1, 1 plus k tau 2. And in this case, Kp is just this. Because again, as t goes to infinity, this drops out, and I'm just left with this guy is 1 over 1 plus k tau 1. You see how much easier it is to do it this way. Questions? Okay, so let's do a little more Laplace transforms. How are we doing on time? We're great in a half hour. Okay, so let's look at the notion of delay. Why am I interested in the delay? If I have a plug flow reactor, then what comes in one end, if there's no reaction, comes out the other end, but it comes out tau seconds later. So in the absence of reaction, what a plug flow reactor does is it gives me a delay of tau seconds. So I want to know how to handle delays. Did you ever handle that?
Sorry, I noticed that I want to make sure
That what?
Like, your function would never exclude the x, yes, it's just like, is that right?
I'm sorry, you have to speak slowly and loudly. So,
Okay, so is it true that when you use the Laplace transform, the final answer will be an x?
my will cannot have an s. No, because remember, I'm either in the time domain or in the s domain. In the final, what I do is I start the time domain, I transform everything into the s domain. That gets rid of the derivatives and the integrals. I do all the algebra and I find the answer in the s domain, and then I have to go back to the time domain. So the answer can't depend on s. S is an auxiliary variable. And notice the final answer has no s's in it. The thing with the tilde at the end, only s's and no t's. When I go back to the time domain, there are t's and no s's. The tilde, which was here, had only s's and no little t's. The answer has only little t's and no s's. All right, so let's do a delay. So if I have a delay, then I'm looking at f of t minus t star. A delay of t star a second. So that's f of t minus t star. That is, when t is equal to t star, then I get the value, as opposed to when, that I had when I came in. So for example, if it's a plug for reactor, t star would be tau. So let's look at the Laplace transform. This is equal to the integral f of t minus t star, e to the minus st dt. Should I close some of these? Is the glare bothering me? One more. Is that better? Okay. So in order to do this, I want to change variables from t to t minus t star. So this is equal to the integral f of t minus t star. And now what I'm going to do is I'm going to take t minus t star here, which means I multiply by e to the plus s t star. So for this to be equal, I have to multiply by e to the minus s t star. Because this times this will cancel out. Here I multiply by e to the st star, so I have to divide by e to the st star. Now it's dt. Now if I want to go from variable t to t minus t star, then I have to subtract t star here. Infinity minus t star is just still infinity. But if you remember, one of the assumptions we had was that f is f for its argument less than 0 was 0. Recall f of t is 0 for t less than 0. So when t is negative, when t is less than 0, then t minus t star is less than 0. So this f is just 0 here everywhere. So I can just start from 0. In which case, this thing is exactly the definition with my variable of f tilde. So f of t minus t star tilde is just equal to e to the minus st star f tilde of s. E to the minus st star came down, and this thing is just my new variable is t minus t star. And in that variable, that's just exactly the definition of f tilde. So for a delay, I just get an exponential e to the minus st star, where t star is the length of the delay. Okay, so that brings us to the point where we can do what's called the final value theorem. So let's do the final value theorem. The final value theorem says the limit as s goes to 0 of s f tilde of s is equal to f It's the limit as t goes to infinity. Okay. So what does that tell me? That tells me something really useful. What it says is, let's say I have a differential equation, and I Laplace transform it. And all I really want to know is what happens at steady state. I don't have to solve the differential equation. I don't need to solve it. As long as I know what f tilde is, I just take this limit and I know the steady state result without solving the equations. Not necessary. So let's see, let's just make sure I got that right. Okay, well, we'll see when we try to prove it. Let's take the limit as s goes to 0 of the f dt tilde. So I'm going to do that in two ways. So first, I know what the f dt tilde is. So this is equal to the limit as s goes to 0 of s f tilde of s minus f of 2. Because here it is. Let's just take the limit. But let's go back to the definition. From the definition, it's also equal to the limit as s goes to 0 of the integral of f dt e to the minus st dt from 0 to infinity. Now again, I'm going to do something that needs mathematical justification, but since this is an engineering class and not a math course, I'm not going to justify it. I'm going to switch the limits. That is, the integral is a limit, and this is a limit. And I'm going to move this limit inside. That requires justification. And there are a set of theorems called the Fubini Theorems that tell you when you can do that and when you can't. The gist of the Fubini Theorems is, if both answers are finite, then you can do it. But sometimes, if one answer is infinite and the other is finite, then you can't do it. So basically, if both answers are finite, then you can switch the limits. That's the gist of the Fubini. So I'm going to move the integral inside, the limit inside the integral. And if I do that, when I take the limit as s goes to 0 of this has no s's in it, but the limit of s goes to 0 of e to the minus st is just 1. When s is 0, it just becomes 1. So this just becomes the integral from 0 to infinity, df dt. And that's easy. That's just f of infinity minus f of 0. So when I can switch the limits here, I have f of infinity minus f of 0 is equal to limit as s goes to 0 is s f of s minus f of 0. So the f of 0 is cancelled. And I have the limit as s goes to 0 of s f tilde of s is equal to f of infinity. The limit as s goes to 0 is f f tilde of s is f of infinity. So, and again, that's really useful because notice I didn't have to solve the equations. So for example, over here, I solved the equation and then I let t go to infinity to find the steady state. I didn't have to do that. I can do it directly from here. Let's do it directly from here. So, 2 CSDRs in series. Let's find CA2 of infinity. Prime of infinity. That's equal to the limit as s goes to 0 of s f tilde of s. F tilde of s, CA2 prime tilde of s. That's CA in prime divided by 1 plus k tau 1, 1 plus k tau 2, times 1 over s, 1 over 1 plus s t1, 1 over 1 plus s t2. Okay? I just took CA2 prime tilde off. Before, whether I go to A or B, I won't start it from here. And now I notice I have an s up here and an s down here, they cancel. And I take the limit as s goes to 0, those both go out when I do the limit. So this just gives me CA in prime over 1 plus k tau 1, 1 plus k tau 2. And therefore, if I want to get Kp, it's just this thing over this thing is 1 over 1 plus k tau 1 over 1 plus k tau 2, which is exactly what I found here, squared or this, without solving the equations. And that's the nice thing about the final value theorem. Questions? Well, one of the assumptions needed for this is I need f to be continuous. For this to happen, I not only need the Fubini theorems, but I also need f of t to be continuous on 0 infinity. So I should have written if f of t is continuous on 0 infinity. Then I need f to be continuous. So let me give you an example where this fails if f is not continuous. So let's look at the example 1 over k, f tilde is k, example when f of t not continuous. Let f tilde of s be equal to k over s, st minus 1. Where t is positive. So notice, when t is positive, then when s is equal to 1 over t, which is a positive number, then this becomes 0 and it blows up. So this is discontinuous. So here I get f tilde of s. Discontinuous. At s is equal to 1 over t, greater than 0. If t were negative, that wouldn't be a problem. I only need to be continuous on 0 to infinity. So let's look at the, calculate the results. So the limit, let's limit as s goes to 0 of s f tilde of s. What's equal to that? The limit of s f tilde of s. I multiply by s, and I said s is equal to 0 is minus k. But what about the limit as t goes to infinity of f of t? Let's see what that is. Well, to do that, I need to look at my table. I need to invert it to check. So let's notice that this is equal to k minus k over s times 1 plus s times minus t. And I wrote it in this form so that it's in the form of line 5. So this is the limit as t goes to infinity of minus k. And then I have 1 over s, 1 over 1 plus s with the minus t. So that from line 5 is just 1 minus e to the minus little t over minus t. The minuses cancel. And this is 1 minus e to the t over t, e to the little t over big T. As t goes to infinity, this thing becomes infinity because it's e to the t. So I have minus infinity times a minus is plus infinity times k is equal to infinity. So notice Here, the limit as t goes to infinity of f of t. The right side is infinity, whereas the left side is minus k. And minus k is not infinity. And that's because I violated f tilde being continuous. And you can note that it violated the Fubini theorem. The Fubini theorem said if one of them is infinity, then it often doesn't, you can't change the limits. Here one is infinity, the other one's not. So I couldn't change the limits. Question? Do we have a picture of this board so I can erase it? Okay, so now that we have the final value theorem, we need the other thing, which is the initial value theorem. And this says the limit as s goes to infinity of f tilde of s. S f tilde of s. The limit as t goes to 0 of f of t. Let's just make sure I got that right. Yes. Okay. So you might say this isn't all that useful. Don't I know what the initial condition is? But the initial condition is built in also. So let's see what that is. Proof. The limit as s goes to infinity of df dt tilde. Well, df dt tilde we said is just this. So that's equal to the limit as s goes to infinity of s f tilde of s minus f0. And now let's go back to the definition. The definition is the integral from the limit as s goes to infinity, the integral from 0 to infinity, e to the minus st df tilde dt is equal to. Well, again, I'm going to presume that I can switch the limits. I can bring this inside. And if I bring this inside, then so if I bring this inside, I take the limit as s goes to infinity of an exponential, e to the minus infinity is 0. So the integral from 0 to infinity of 0 dt is 0. So it's 0 when I bring this in. Again, I'm presuming I can switch the limits for meaning. So this minus this is equal to 0. So therefore, the limit as s goes to infinity of s f tilde of s is equal to f of 0. So we have both the, and the reason I give you both these theorems is to notice the duality of t and s. We said we've got the t domain, we've got the s domain, and we work from one or the other. And they're somehow rules of each other, meaning they have the same information. They're encoded with the same information. They're just presenting it in different ways. And you can see that the value of f at infinity is related to f tilde at 0. The value of f at 0 is related to the value of f tilde at infinity, s f tilde. So there's a duality. When one is 0, the other one's infinity. And there's a duality between them. But they have the same information in them. What we want to do is pull out, extract the t information, but do the algebra in terms of s because it's a lot easier. And we want to be able to go back and forth. Back and forth. Questions? Yeah.
When you're going back and forth with the table,
It's magic. It's magic.
It's magic. But it's likely or even maybe necessarily that you'll be using two different lines from one way to the other.
Oh, well, you're certainly going to be on two different lines because you have individual terms that you're transforming in the beginning, and then you're doing algebra and getting a new result. So you need a different line to go back. As we'll see next class, I won't get to it this class. We can't have a table that's infinitely long. So a lot of times we're going to have a result that looks complicated in S, and we're going to have to do a little algebra to try to break it up into a sum of terms, each one of which is in the table. You can't expect the result you come up with automatically in the table because it might be the sum of 5 terms, each one of which is in the table. So we're going to do that breakup. Breaking up is hard to do. We're going to do that breakup next time, but we're not going to do it today because I only have 10 minutes left. Questions? I may introduce it today. Let's do the level problem. So if you remember, let's do the level problem where so I want to control the level here. I want to know the level of it. So we have the LVT, let's call the height, L, level, VT times A. That's the change in volume, is equal to V in minus V out. And if you're, what we're going to assume is that V in undergoes a step change at t equals 0. And we said V out was equal to K square root of L. And we derived that from Bernoulli's equation last time. And so, and actually I want to divide through by A. Let's leave A. Sorry. Okay, so I have the LBT. The LBT is equal to V in over A minus K over A square root of L. So this is exact. And then I want to linearize. So when I linearize, we said this was equal to K times the square root of L at t less than 0. I'm linearizing about t less than 0. Plus the derivative, which was 1 over 2 square root of L t less than 0. Times L prime. That's the linearization. So now I have to linearize. We'll say the L t less than 0 dt is equal to V in prime. I'm sorry, V in t less than 0, t greater than 0, less than 0, over A minus K over A times the square root of L t less than 0 plus 1 over 2 square root of L t less than 0 times L prime. This is exact linear. This is exact linearized. I'm sorry. I should do this t greater than 0. Let's do t greater than 0. This is t greater than 0. This is the exact value, the exact equation t greater than 0, the linearized equation t less than 0. Now I take the exact for t less than 0. That's the L t less than 0 dt is equal to V in t less than 0 over A minus K over A times the square root of L of t less than 0. That's the exact for t less than 0. I didn't have to linearize it. Now I take this and I subtract this. When I subtract them, this term cancels, and I'm left with the L prime dt, because L minus L at t less than 0 is L prime, is equal to V in prime over A, plus 1 over, plus K over 2A root L t less than 0 times L prime. So I bring this to the other side of the equation, L prime t. And I should have had, and there's minus. It's a minus. It's a minus up there. So I've got plus k over 2a root 2a root L of t less than b. That's the coefficient. Times L prime is equal to v in prime over a. So this is all algebra we've done before. From this point on, we're going to use Laplace transforms. The Laplace transform, I have L prime tilde times, I'm going to call this whole thing alpha, so I don't have to keep writing it. S plus alpha is equal to v in prime over a. Now, I want to get it in the form of 1 plus s times something. So I divide by alpha. So I factor out the alpha. It's equal to v in prime over a. Is that clear? I just factored out an alpha. And this is in the form I like. So now I have L prime tilde is equal to v. And now I need to take a tilde here. V in prime tilde is v in prime divided by s, because it's a step function. And now I have 1 over alpha, and here I have 1 plus s times 1 over alpha. Yes?
How did you get, so that's second line you have L times S plus alpha.
I call this thing alpha, so I don't have to keep rewriting it. I'm sorry?
Where did the S come from?
I take the Laplace transform of the derivative and I get s times L prime. Okay. All right, so now I look at, this is again line 5, good old line 5. So this tells me that L prime of t is equal to v in prime over a alpha. And this tells me that line 5, good old line 5, I just get 1 minus e to the minus t over 1 over alpha. Again, no algebra, just reading it off the chart. So have we demonstrated why this is useful? Questions? Okay, so as I mentioned a few minutes ago, a lot of times, these charts are not infinitely long. Sometimes you're going to get things that are linear combinations of things in the chart. Let me give you an example, and I only have time for the example. Let's say I have 1 minus s minus a, s minus b. So in kinetics, you probably learned to solve partial fractions, that I can write this as a over s minus a plus b over s minus b. So I take something complicated and I write it as a sum of 2 terms. And to calculate that, I multiply top and bottom by s minus a, s minus b. And I get 1 is equal to a times s minus b plus b times s minus a. And if this has to be true for all values of s, then I can equate the coefficients of like powers of s on both sides. So s to the 0 tells me 1 is equal to minus ab minus ba. And the power of s to the 1 tells me 0 is equal to a plus b. So that tells me, plus as and bs. So it tells me b is equal to minus a. And if b is minus a, this is equal to minus ab plus aa. So I can factor out the a. This is a times a minus b. And so I don't have to erase another blackboard, which I don't have time for. I get a is equal to 1 over a minus b. And b is minus 1 over a minus b. So I have 1 over s minus a, s minus b. s minus a minus 1 over s minus b. So I've broken this up into two terms. So imagine that this is my answer. But I don't have this in, let's say I didn't have this in the table. I can break it up into two terms that I do have. And this term I look up in the table, this term I look up in the table. So this is an example of how you answer maybe a linear combination of things in the table. And what we're going to talk about next time is how to do this breakup in general, not just for this one example. Okay, and then next time is tomorrow. You may think it's a Thursday, but City College says it's a Monday.